Section 9.6, Buoyant Forces and Archimedes Principle. Our objectives are to state Archimedes Principle, which is right here, and explain its physical origins, and apply Archimedes Principle to floating and submerged objects. The Archimedes Principle in words is an object completely or partially submerged in a fluid is buoyed up by a force, a buoyant force, with magnitude equal to the weight of the fluid displaced by the object. So mass of fluid times gravity, which is the weight of the fluid, which is actually density of the fluid times the volume displaced times gravity. And that acts upward. And this is called the buoyant force, B-U-O-Y-A-N-T. And not a mysterious new force that arises in fluid. It arises from the pressure differences between the upper and lower sides of the object. Remember, if you have a pressure 1 down, or pressure 1 up here and a pressure 2 down here, pressure 2 minus pressure 1 is equal to the density of the substance times the mass. Okay, it's rho GH. And then multiplying that by area, you get the difference in the forces. Force 2 and force 1 is going to be rho G, and is going to be pressure times area. So rho GHA, which is rho GV. So that makes the net force, which is force on the bottom minus force on the top, equal density of the fluid times the volume displaced by the fluid, volume of fluid displaced times gravity. Now that we know what this buoyant force comes out to be, we can use it in Newton's second law. So we'll have the sum of forces be a lot of times will be the buoyant force, which is density of the fluid times the volume of the fluid displaced times g, and that usually is going up, and so minus mass times gravity going down. And then sometimes if the thing is resting on the bottom of the water or something like that, we may have a plus t pulling up, or a normal force pushing up from the bottom of the surface. And then all of that is divided by the mass of the object that is either sinking or floating. If the acceleration is 0, then you can ignore the mass, or you can leave the mass out of the equation and just have this top part. And that is an equilibrium condition. And in equilibrium, either the object would be stationary or would be moving at constant velocity. If the object is completely submerged, of course, the volume of that object is equal to the volume of fluid displaced. But if you have a situation where the object is floating, then the volume of fluid displaced is just equal to the part of the object that is under the water. There's a bunch of applications they mention here. Buoyancy control in fish. A fish has an internal swim bladder, and it can fill it with air, I guess, so that it can float or maintain a neutral density. Now, I guess you wouldn't have to fill it with air. All you'd have to do is basically either use your muscles to pull it apart, which would reduce the pressure, or relax the muscles to let it collapse, which would increase the pressure. Then they talk about cerebrospinal fluid, and apparently the brain floats in a fluid of density around that of water, and as long as if that fluid ever gets drained, the nerves and blood vessels of the brain are placed under great strain. And then I guess if you've ever checked the antifreeze in a car radiator, there are balls that have mixtures of antifreeze and water in them from 5%, 10%, 15%, 20%, etc. And depending on which balls float to the surface, you get a measurement by looking at how many balls there are on the surface of how much antifreeze there is in the tank. And some car batteries use the same kind of technique with a magic dot. So when the orange ball floats to the top, you can see an orange dot indicating that the ball is sufficiently charged. And then when the orange ball sinks down, that creates a appearance of a black dot, which means the battery is not sufficiently charged. So Quick Quiz 9.5, atmospheric pressure varies from day to day. The level of a floating ship on a high pressure day is higher, lower, or no different than on a low pressure day. And the answer is choice C. The level of a floating ship is not affected by atmospheric pressure. The buoyant force results from the pressure differential in the fluid. On a high pressure day, the pressure at all points in the water is higher than on a low pressure day. Because water is almost incompressible, however, the rate of change of pressure with depth is the same, resulting in no change in the buoyant force. And Quick Quiz 9.6 asks, the density of lead is greater than iron, and both metals are denser than water. If the buoyant force on the solid lead object is the buoyant force on the solid lead object greater than, equal to, or less than the buoyant force acting on the solid object of the same dimension. Here, let's remind you that the buoyant force is the density of the fluid times the volume of fluid displaced times gravity. Whether you have iron or lead, if it's the same dimensions, the volume displaced by it is going to be the same. And since both lead and iron are denser than water, both objects will be fully submerged. And since they have the same dimensions, will displace equal volumes of water. Hence, the buoyant forces acting on the two objects will be equal.